Okay, so here's my chapter 11 homework. A couple problems I didn't finish it was way late at 9. I was gonna finish the other two this morning, but they're not done. But here's the motion of a particle defined by x equals 6t to the fourth, yada yada yada. This one's pretty simple. To find the position, velocity, and acceleration, you just do the derivatives and input your acceleration at time 0 here, or excuse me, acceleration of 0, and then you find the obviously your time is not going to be -1/2, so you choose 2/3. Then you go back into your equations, put in 2/3, you get 0.2593. There's no, oh, there is meters. When I did this, I thought there weren't any units, but these are meters. And then this is meters. You can, anyways, so this one, you just manipulate the problem a little bit. Here's your constant acceleration equations. Dx dt equals v0 minus kx. Because that is the formula we were given. I was like, where did I get that? Anyways, so you do the integration because we're trying to find our t value. And then we get blah, 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 blah. And then we get something that looks like this. We go and find our acceleration, which is just the derivative of the velocity. We find this -k dx dt. We know dx dt is really just v, so we put that back in there. And so we were given v0 minus 2700, which we found over here. I didn't explain this problem in the right order. Anyways, and then you go and put that back in this function after you find the, oh well, this is part A, initial acceleration. And then part B is finding the time. This one's probably my favorite because I think this is cool. The other one's useful too, but where to begin? These are your givens. This is also a given. Then you separate it out to integrate it, so you can get your position. This is U substitution. And then this is what I get when I solve it all out. I'm doing integration here because we're trying to find our t. We've got dv, okay? So then we take our v initial, v finals, and input that in here. We get, so that we can figure out what our v final is, because we know how much time it took, which was given to us as 3 seconds. And then we find our v final, 12.8629. We've got this problem, which I was trying to solve. Really wasn't making any sense to me. I need to look over the solutions manual really, because I didn't even understand that one. So, but it's pretty, I mean, it's just like the other ones, so I don't know why I'm having such a tough time, but come back to that one. This one's sort of simple too. You just take this formula and you work with it. R equals R. So radius versus the total radius. Big R is the radius of the Earth. R is the distance from the center. me solve for that. Kilometers per second. I should probably just change the unit, but you do the integration here so that you can figure out what your C is if you need to get rid of your, what you can do with your C, and then put it back in the formula with no plus C here. This is the parachute one. This one's pretty cool. We're asked to find the total time of the initial deceleration. So you take the position, you figure out the change in position, you put in a change of position formula, and then you solve for your acceleration, which is negative 103.33, which I answered there. V naught plus. So this is so we can find our time, now that we know how much time that took. Now we do the same thing for this section. And then we find that. We do the same thing for this section because, well, it's not exactly the same. We have constant acceleration through here. So we don't have to solve for acceleration. Well, there's really no acceleration, is what I should have said. So we use the first, well, we just use the normal velocity times time, tells you how much change in position you have. Anyways, so now we just need to find the last segment, change in 30, and then we have to go back to the one we used on the first one, find our acceleration. So, and then we put it in here and solve for our t. So our total time is 44.78 seconds, and our initial deceleration is 103.33 meters per second. Oh, apparently I just skipped that one for now. Let's come back to this. This one's really fun. These are the formulas. You set it up. Y max equals this, and then you, man, I'm too tired to explain all this, and it's hard to say this fast. Anyways, so you get that, and then you solve for your t. You put in your values here, and then you get 1.3941. For your y, this tells you how high it was when it comes to the pattern. And then you get 0.937 meters, which seems like a decent strike zone area. Y max, this tells you the max it's going to reach is within this zone, so we're okay because that was part of the parameters. You know, it needs to be taller than 1.8 because it's softball, I guess. There's that problem. This one was a little more intense, so you had to set it up. First of all, figuring out your angle here. And then you had to figure out what's your distance. X would be here and your distance Y here. So you can put in the values back into the other function that you created to determine if they'll land between those 2 points. Or what velocity you need for it to land between those 2 points. So, yeah. So this tells you the slower velocity and the slower time. Or well, that's not slower time, that technically takes less time. And then this is your faster velocity. And it takes a little bit more time because that's the top range of this. And then the first one's at the lower range of that. These ones are really simple, fortunately. You set it up, your acceleration normal equals 3g. I forget what this letter's called. Your radius from your axis of rotation is 5 meters. So you just put that in there and solve for v. You get 12.131 meters per second to create a 3g force. Same thing here, except for we're just solving for a different aspect of the problem. And we find it as 1467.8899. And then I need to do these. I was going to do these this morning, but I I'm not, so I need to come and finish them.